Hello class, let's compare three different fin geometry with these given material and information. So it is going to be aluminum alloy, thickness is given, so thickness is 3 millimeter, length is 15 millimeter, base temperature 100, T infinity is 20, convective coefficient is 50, and conduction, because it is aluminum alloy, it's around 185. And I'm supposed to compare fin efficiency and heat transfer rate for these straight fins: rectangular, triangular, and parabolic profile straight fins. When I say straight fins, I mean this one, and this one. So I'm going to compare these three. So one way is going to be designing all those fins and changing the geometry in a way they'll have same volume or mass, and then compare with each other. Another way is going to be the way I'm going to do it. Let's see what is my procedure. So first of all, let me write the heat transfer rate, which is going to be fin efficiency times h times area of fin. Here we are talking about one fin, and temperature difference, which is base temperature, minus T infinity. For the first one, which is rectangular one, I need corrected lengths. So corrected lengths is necessary because fin efficiency is based on the corrected lengths. So let's do it. Corrected length is going to be length plus half of thickness. It is 15 millimeter plus 3 millimeter thickness divided by 2, which is going to be 16.5 millimeter. Let's calculate M. M is going to be 2h divided by kt. Why? Because it's given here. M is 2h divided by kt. So, which is going to be 2 times 50. H is given here in this question. K is 185, and thickness was 3 millimeter, 0.003. So M is going to be 13.4 meter power negative 1. So let's check efficiency formula for rectangular straight fin. Efficiency formula is tangent hyperbolic ml divided by ml. So it is going to be tangent hyperbolic MLC divided by MLC. Let's do it. It is going to be, because I don't know what is tangent hyperbolic of that, I'm going to calculate using Wolfram Alpha website. So mistake. So tangent hyperbolic of ML. ML was 13.4 times LC was 16.5. So 0.001 0.65. So let's see what is the value. It is going to be 2.2. 0.22. Let's write it here. It is 0.218 divided by MLC, which is 13.4 times 0.00165, and if you do the calculation, it is going to be 0.982. So this is my efficiency for rectangular straight fin. Now I need to find area of a straight fin, which is going to be 2WLC. Why? Because here it's given 2WLC. So it is going to be I'm going to consider W as a 1 and just removing all the values for depths. So W times LC was 0.0165, which is going to be 0.033 meter. This is area, it's supposed to be meter square, but I removed W, so it is going to be meter. And therefore Q dot is going to be IHAF T base minus T infinity, which is 0.982. I just calculated. H was 50, it's given, times area of the fin was 0.033, times temperature difference, base is 100 and T infinity is 20, so it is going to be 80, and Q dot is going to be 129.6 watt per meter. Again, meter is supposed to be meter square, but I removed that W. What about volume? Because I want to know what's the volume. Thickness, length, depths. And it is going to be 4.5 times 10 power minus 5 meter square for the volume. So this is rectangular straight fin. So this is all the calculations I needed for rectangular straight fin. Let's start with a triangular one. Let's go back. Triangular, instead of LC, which I had for rectangular, I have L and M. So let's find everything for triangular. So L is going to be again 0.015, so we don't have any change and conversion to LC, and M was 13.4. So ML for this one is going to be 0.201. So let's check the formula for efficiency. It is this 1 over ml and Bessel function of 2 ml divided by 12. So the formula for efficiency of this fin is going to be 1 over ml times I Bessel function of 2 ml divided by 0 Bessel function of 2 ml. Okay, now let's find this. 1 over ml was 0.201, and we need to find Bessel function. So what is the value for 2 ml? 2 ml is going to be 2 times this value, 0.201, which is going to be 0.402. So let's find Bessel function of 0.4. I have a table for Bessel function of 0.4. 0.4 is going to be this one, and I need to find this value. So let's see, e power minus 0.4 times Bessel function of 0.4 is going to be 0.6974. Therefore, Bessel function of 0.4 is going to be 0.6974 divided by e power minus 0.4. Let's see what is going to be this. Again, let's go here and find a value. So I just forget it. So 6974. So 0.6974 divided by e power negative 0.4. Let's see what's the value. So 1.04. So this one is 1.0404. Let's find the other one. So 0.0368 is going to be equal e power minus 0.4 times the other Bessel function. Again, Bessel function at 0.1 is going to be 0.1368 divided by e power minus 0.4. Let's do that one. 1368. So point 1368. Let's find this one. So the value for this one is going to be 0.204. Let's write it down here. So 0.204, and if I calculate, this is going to be 0.978. So this is fin efficiency for triangular, sorry. And let's calculate fin area. What's the formula? Fin area formula is here. So 2w, which we don't put any w, square root L power 2 divided by half of the thickness power 2. So 2w L power 2 plus T half power 2, which is going to be 0.030 meter. Again, meter squared, because I'm not using W, it's going to be meter. And finally, Q dot is going to be fin efficiency 0.978 times area 0.03 times H, which is 50, times temperature difference, which is 80, and it is going to lead us 117.3 watt per meter. This is heat flux, and the volume is going to be TL divided by 2, again multiplied by W, which I am not going to include, and it is going to be 2.25 times 10 power minus 5 meter square. Okay, so this one was for triangular shape. Let me write triangular straight fin. Finish this one. Now let's go and do it with this color. For the parabolic one, let's check the formula for parabolic. M is same as the previous one. I'm going to use L, so no calculation in that part. Let's calculate fin efficiency. So fin efficiency for the parabolic one is 2 divided by 2 ml power 2 plus 1 plus 1. And if I put all the values in and plug in, 6963, so 96% is going to be a fin efficiency. Area for fin is going to be this, and we have C1. To get C1, you need to use the other formula, and you have everything there, so it is going to be 0.03 meter. It's very similar to the previous one. So Q dot is going to be fin efficiency 0.963 times area 0.03 times H 50 times temperature difference, which is 80 degrees, and heat transfer rate is going to be 115.6 watt per meter. And volume for this is approximation. I'm going to approximate divided by 3. The volume is going to be 1.5 times 10 power minus 5 meter square. And this is parabolic straight fin. Let's have all of them at the one page. Now you can see that fin efficiency for the rectangular one is 98%, for triangular 97%, and for parabolic 96%. So the lowest efficiency belongs to the parabolic one. But if you check the volume, the rectangular one has the highest, and then triangle is almost half of it, and the parabolic one is even lower, and half of that is going to almost half of that volume. And although the volume is half, but the efficiency drop is like a less than 10%. So overall, if you compare Q dot over volume, you are going to have a better comparison between different fins. So this is much easier than designing all the shapes of the fins or geometry of the fin in a way to have same volume and then compare it, which is difficult. So basically what I'm suggesting, do the comparison for the any shape or size you want, divide the heat flux by the volume of that heat sink or fin, and then this value is going to be good representation to compare different fin types. Okay, I hope you learned something out of it, and see you next time.